notice you have seen this before and this. We are at section B, entitled Thermal Physics. And in this video, we will be talking about latent heat, which is defined as the heat required to convert a solid into a liquid or a liquid into a vapor without a change in temperature. That is latent heat. But we will be dealing more with specific latent heat that has to do with 1 kilogram of such a substance. So far, we have completed these 7 formulae on the left that you see here. Up to this point, these 7. And now we will consider formula 8 up here. Now, latent heat is the heat required to convert a solid into a liquid or a liquid into a vapor without a change of temperature. And of course, if we talk about specific latent heat, we will be dealing with 1 kilogram of a substance. The 2 new formulae we have are EH, that is heat energy, is equal to the mass times latent heat of vaporization, or heat energy is equal to the mass times the latent heat of fusion. LV is the specific latent heat of vaporization in joules per kilogram. LF is the specific latent heat of fusion in joules per kilogram. EH, of course, is heat energy in joules. M by now we know is mass in kilograms. V is the potential difference or the voltage in volts. I, current in amperes. T, time in seconds. And P, power in watts. EH in both of these 2 equations up here can be replaced with either VIT or PT. Now also note that in these formulae here on the left, there are no delta theta, which means that no change of temperature is involved. And that is why we said when we define latent heat or specific latent heat, that change in state from a solid to a liquid or a liquid to a gas, it must occur without a change in temperature. Consider for a moment that we have a graph like this. On the y-axis we have temperature, and on the x-axis we have energy. Suppose you are told to calculate the energy required to convert some ice at negative 15 degrees Celsius to steam at 120 degrees Celsius. You will be given the mass, how much? Well, first of all, you need to make a sketch of what is required. We will set up the melting point and the boiling point of water. And then we will assume that somewhere down here is negative 15 degrees Celsius. We will have to heat it up until it reaches the melting point. Here you have all ice. As you add energy to it, going this way, the ice gradually becomes water, still at 0 degrees Celsius, until all the ice has become water. And then you add heat to the water, and the temperature of the water now increases until it reaches its boiling point. If you keep adding energy, then all the water at its boiling point will eventually become steam at its boiling point. And then if you were to capture the steam and heat it, the steam itself will increase in temperature. This is the boiling point of water. This is the freezing point of water, or the melting point of ice. Notice that at this point here, it is solid ice. At this section here, it is just liquid. And up here, it is gas. In all three of those situations where you have a change in temperature and you want to find the energy, you will use this same formula, where EH is equal to MC delta theta for a solid, and for a liquid, and for a gas. So essentially, you are using the same formula 3 times. You will notice, though, that at this point, we have no change in temperature. No change in temperature. We do have a change in state, where a solid becomes a liquid if you are going in that direction, adding heat, or if you are removing heat, the liquid becomes a solid. LF is called the latent heat of fusion, or rather the specific latent heat of fusion. It doesn't matter which direction you are going in. It is the same number. And of course, up here you have LV, which is the latent heat of vaporization. So if you have water at its boiling point and you boil it and it all becomes steam, 1 kilogram will take a certain amount of energy to do that. However, if you had the steam at 100 degrees and you cool it down, then you would have to remove that same amount of energy to make it into a liquid at its boiling point. Now, in all of these formulae, you can replace EH with PT or VIT, depending on what you are given. So if you begin at 15 degrees Celsius down here, and you want to find the energy that will convert, let us say, 8 kilograms of ice to steam at 120 degrees Celsius, you start down here, you will have to heat up the solid. Then you will have to change the solid into a liquid. Then you will have to heat up the liquid going this way until it reaches its boiling point. Then you will have to boil off the liquid, vaporize it. And then once it reaches here, you have now all vapor at 100 degrees. And then finally, you will have to heat up the vapor to, say, 120 degrees. So if you had such a question, you will have to do 5 little parts of the question and then add them up to get your final answer. Don't get worried, CXC on an exam will not give you such a question like this. Let us look at example 1. How much energy will it take to melt 2.3 kilograms of ice at 0 degrees Celsius to water at 0 degrees Celsius if the specific latent heat of fusion of ice is 334 kilojoules per kilogram? So we will make a little drawing to find out where we are and where we need to get to. So if we are dealing with water, the melting point of ice is 0, the boiling point of water is 100. So we make a little sketch like that, and then we put in the starting point. Where are we starting and where do we need to end? In this case, we are not moving out from here because it says at 0 degrees Celsius. So you start out with 2.3 kilogram of ice at 0 degrees Celsius. So you are starting here at A, that's our starting point. And you want to convert it to water at the same 0 degrees Celsius. So you're not going up anywhere up here. No, we're not going up there. We are going as far as that. So all we are doing is converting the ice at this point to water at this point. We are going from point A to point B. All we are concerned with is this little part of the graph. Now, we know that the mass is 2.3 kilograms. We know that the latent heat of fusion of water is 334 kilojoules per kilogram. And we want to find how much energy we would have to add to that ice at 0 degrees Celsius to make it water at 0 degrees Celsius. And so we have a very simple equation here. EH is equal to MLF. We know these two on the right, so we will just substitute them, and we get an answer of 768.2 kilojoules. Since this has two significant figures and this has three, we can only have two significant figures in our answer. So we have to round off where that 6 is, which is the tens position, and we get 770 kilojoules, and that should suffice for CSEC. However, just to be on the safe side, since we know we are rounding off at the tens position, we take half of that position as our answer, and we represent our answer better as 770 plus or minus 5 kilojoules. Now, that one was fairly easy. This is correct too, but this is the one that CSEC accepts. Let's look at example 2. After a liquid begins to boil, so it is at its boiling point, it was found that 356 grams boiled off when 768 kilojoules of energy was added to it. What is the liquid's specific latent heat of vaporization? So let us make a little sketch like what we see here. Let's see where we are starting and where we need to end up. If we were dealing with water, that would be 100 degrees. But it may be another liquid, so it does not necessarily have to be 100 there. Suffice it to say, though, that the liquid has begun to boil. So we are at A. Or we vaporize 356 grams. When 768 kilojoules of energy was added at this point. So we want to know what is the specific latent heat of vaporization of that liquid. So let's see what we know. We know the mass is 0.356 kilograms. We know the heat that we supplied to this liquid at its boiling point is 768 kilojoules, and we want to find the latent heat of vaporization. So we know that EH is equal to MLF. We make LF the subject of the formula, and we substitute the numbers we are given, and the answer from our calculator is 2,157.303 kilojoules per kilogram. Well, we cannot leave it like that. We have three significant figures here, three here, so we need to round off the three significant figures, that is at this point here, and so we get 2,160 kilojoules per kilogram, and that should be sufficient for CSEC. But let's just make doubly sure. Since we are rounding off at the tens position, we take half of the 10, half of that position, which would give us 5, and we can better express our answer as 2,160 plus or minus 5 kilojoules per kilogram. So that is the latent heat of vaporization of this liquid. This answer here is correct too, but CSEC wants that format. Example 3. A liquid has a specific latent heat of fusion of 245 kilojoules per kilogram. calculate how much energy must be removed from 850 grams of this liquid at its melting point to convert it to a solid at the same temperature. So remember what I said, make a little sketch. So what are we dealing with? We are dealing with the melting point. So essentially, we are just dealing with that. We have 850 grams of this liquid. So this is the melting point, that's the boiling point. We are starting here at A, 850 grams. We are going in that direction. So we have to remove energy to change the liquid to a solid at its melting point. So we will end up at B. What are we given? We know the mass of the liquid we are dealing with. It's 0.85 kilogram. We know the latent heat of fusion is 245 kilojoules. We want to find how much heat we need to remove from this liquid to make it a solid. So let me make something quite clear here. If you are going in that direction or you're going in this direction, whether you're adding heat or removing heat, it is called the latent heat of fusion. And the same thing applies up here. If you go in that direction where you add heat to change a liquid into a gas, or you remove heat to change a gas into a liquid, it is still called latent heat of vaporization. Even though you may not actually be carrying a liquid to a vapor, you may be removing energy and carrying a vapor to a liquid. We know that EH is equal to MLF. We know LF and we know M. We will just substitute the numbers we have. And from our calculator, we get 208.25 kilojoules. Two significant figures, three significant figures. Our answer can only have two significant figures, so we have to round off at the position where that 0 is, which is the tens position. So we get 210. And as I said, that should be acceptable for CSEC, but just to be sure, since we are rounding off at the tens position, we take half of that position, which will be 5, and we can better state our answer as 210 plus or minus 5 kilojoules. That is the amount of energy we need to remove from the liquid to make it a solid. This is also correct, but we will use that format for CSEC. Now we will consider a much more complicated question, which requires the use of both specific heat capacity and specific latent heat. In the last video, we dealt with specific heat capacity. And so far in this video, we were dealing with specific latent heat. Let's combine the two together and do one question, which will put it all together. And so this, I hope, will help you to clearly understand how to do these types of questions. You are to calculate how much heat energy it will take to convert 670 grams of a solid at 11 degrees Celsius to a gas at 150 degrees Celsius if the melting point of the solid is 25 degrees Celsius and the boiling point is 130 degrees Celsius. And you are given the following data. Specific heat capacity of the solid. You are also given the specific heat capacity of the liquid. You are given the specific heat capacity of the gas. You are given the latent heat of fusion and the latent heat of vaporization of this material we are dealing with. Now, first thing is to always remember to make a sketch so you can clearly understand what the question is asking. Now, this is not the sketch that we are actually going to use, but it will look something like this. Two axes. You have an energy axis here on the x-axis and a temperature axis here on the y-axis. We put in the melting point, we put in the boiling point, and we draw in This line here for the solid, that one where the solid is changing to a liquid, this one where you have all liquid, that one where the liquid at its boiling point is becoming a vapor, and then here where you are heating up the vapor. So you make a little sketch like that to understand where we are and where we need to go. So this is the actual sketch we are going to work with. Melting point, boiling point. We are starting a little below melting point. Here we have no change in temperature, where the solid is becoming a liquid if we are going in that direction. Here we are heating up the liquid. At this point, the liquid has reached its boiling point. If we continue that way, we are vaporizing the liquid until we have no more liquid. And then if we heat the vapor, we are now heating up the vapor. As I said, this is our boiling point. This is the melting point. So where are we starting? We are starting somewhere here, below 25. We are beginning at 11 degrees Celsius, and we need to go to 150. Now, this here is 130. So 150 may be somewhere here. This is just a sketch. At this point, we have solid. At this point here, we have liquid. And at this point here, we have gas. In all three of those situations, if you need to calculate the energy either going this direction, heating it up, or coming in the opposite direction, cooling it down, in all three cases, you would use the same formula, which is EH is equal to MC delta theta. Of course, the C and the delta theta may be slightly different. And then here where you don't have a change in temperature, and up here where you don't have a change in temperature, you are basically using the same formula, which is EH is equal to MLF, or EH is equal to MLV. So in a sense, we're actually using two formulas. One of them 3 times and the other one twice. First part of the question, we are moving from 11 degrees Celsius to 25 degrees Celsius. That is to say, we are moving here. We are heating the solid to its melting point. And we have the data. We know the mass is 0.67 kilograms. We know the change in temperature is 14 degrees. We know the specific heat capacity of the solid is 220. So when we put all of that in the formula, EH is equal to MC delta theta, we get 2063.6, and we round that off to 2060 joules. That is the amount of heat energy it will take to heat up the solid at this point here, the first part where we begin. Now we need to melt that solid at its melting point, 25 degrees Celsius. We know the mass is 0.67 kilograms. We know the latent heat of fusion is 870 joules per kilogram. EH is equal to MLF. Substitute the numbers we are given, and we get the rounded off value of 583 joules. So now we are at this point here. We have reached here. Continue. We have to heat that liquid from 25 degrees Celsius to 130. So from 25 to 130, the change in temperature is 105. It is the same mass. The specific heat capacity of the liquid is 350 joules per kilogram per degree Celsius. We have a formula that says EH is equal to MC delta theta. Substitute the numbers, and our rounded off answer is 24,600 joules. That is this piece here. So it will take that amount of energy to heat this mass as a liquid at its melting point to a liquid at its boiling point. Now we need to vaporize that liquid. So we are now at this section here. It is the same mass, and the latent heat of vaporization is 1,400 joules per kilogram. And we know that EH is equal to MLV. We substitute the numbers we are given, and we get 938 joules. So now we have all vapor at this point. We are at 130 degrees. We need now to heat that vapor, the vapor itself, to 150 degrees. So from 130 to 150 will be 20 degrees Celsius. We know the mass. We know the specific heat capacity of the gas, C, which is 250 joules per kilogram per degree. We know that EH is equal to MC delta theta. Substitute that in the formula, and we get a rounded off value of 3,350 joules. Well, think about it. We calculated the energy here and there and there and there and up here. And you want to know how much energy it will take to change 670 grams of this material from a solid at 11 degrees Celsius to a gas at 150 degrees Celsius. So we did each part separately. All we have to do now is add them up. And we find that we get 32,000 joules, or we could say 32 kilojoules. And we have our margin of error here, since we are rounding off at this, at the ones position. So it may look kind of complicated, but you think about it carefully, it's not that difficult. You have to do little pieces, and really we were using only two formulae. EH is equal to MLF or MLV, that's one, and EH is equal to MC delta theta. For CSEC paper 2, questions may involve only 3 of these parts. It wouldn't be as complicated as we just did. For one, that will take too long, and two, if you could do 2 parts, let's say one that involved EH is equal to MC delta theta and another part that involves EH is equal to MLF, then CSEC will assume that you could handle the other 3 parts. So let's look at that exam question from a past CSEC paper, and they even make it much easier than what we just did. So the question is, it's adapted from May-June 2013 paper 2, question 2C. A physicist converted 8.0 kilograms of water at 33 degrees Celsius to steam at 100.0 degrees Celsius. Assuming no heat is lost, calculate the amount of energy needed, and they have this in 3 parts. 1, to heat the water to 100.0 degrees Celsius for 3 marks, and then to heat the water from 100 degrees Celsius to steam at the same 100 degrees Celsius for 3 more marks, and then they want you to find the total energy in megajoules required to do those 2 things. You are given the specific heat capacity of the water and the specific latent heat of vaporization of water. So we make a little sketch. Melting point, boiling point. In this case, we are dealing with water, so this will be 0 and that will be 100. We are starting somewhere at 33 degrees, which will be here, and we need to go over there. So we need to heat this water from 33 degrees to 100 degrees, and then we need to vaporize all that water at still 100 degrees. So really, it's just 2 little parts you have to do here, as opposed to the 5 parts we just did in the previous question. So the first part, we know that M is 8.0 kilogram. We know that delta theta is 67 degrees Celsius because you are moving from 33 to 100. from 33 to 100. We also know that the specific heat capacity of water is 4,200 joules. How much energy is required to do that? EH is equal to MC delta theta. We substitute the numbers we are given, and we come up with this answer, which rounded off to megajoules is 2.3 megajoules. You don't need to carry it to megajoules at this point, but we can do that while we are on it. So that is the first part. From here to there requires 2.3 megajoules to heat the water from 33 to 100. Now, we need to vaporize that water, all 8.0 kilogram of it, at 100 degrees to vapor at 100 degrees. We know the latent heat of vaporization of water is 2,300,000 joules per kilogram. We know the mass, and so we know EH is equal to MLV. We substitute the numbers we are given, and we get a rounded off answer of 18 megajoules. So that's the answer to the second part of the question. How much is it to convert the hot water at its boiling point to vapor at its boiling point? And then the last part of the question is, what is the total energy required to do that, beginning from where we started here at 33 to where we ended up here? So you just add those two. And so recall that now we are adding 2.3 megajoule to 18 megajoule. We have to round off at the position where we first meet an uncertain digit, which is in the ones position. And so even though we get 20.3, we have to round off here, and that would give us 20. And because we are rounding off at the ones position, we take half of the ones position, which is 0.5. And so our answer is 20 plus or minus 0.5 megajoules. So as I said, this is an actual CSEC pass question. You can expect something like this. As it stands now, we have completed all 8 of these formulae from section B, thermal physics. So that brings us to the end of the formulae in section B, thermal physics. Next, we will move on to the formulae in section C, which deals with waves, specifically sound and light. And that brings us to the end of this video, Physics 15.